from 1 to gazillions, divergence, right? Branching upon branching upon branching upon branching. Every time you have the next generation of branching, the vessel is getting smaller and smaller and smaller in diameter until we get down to the microscopic level. In general, we're going large artery to medium artery to small artery, and small artery is not another name for arterial. Yes, an arterial is a small artery. It is the smallest. That's why it's arteriole. Teeny, teeny, tiny. The very end of the arterial system. But in sequence, it goes small artery to arterial. And then through the capillaries. And then convergent. The venous system is convergent. We start with many gazillions, and we converge until we're down to 2, the 2 vena cavae. So it's sort of like unbranching or debranching. So you're going venules to small veins to medium to large. So this is divergence. This is convergence. The vessels that represent the largest surface area are the capillaries. Right? So as you move towards the capillaries, surface area is going up. As you move away from the capillaries, surface area is going down. Here's total surface area through each section of the arterial tree and the venous tree. And you see the surface area peaks at the capillaries and then goes back down. Velocity is directly related to surface area. As you spread out that blood over more and more vessels, the speed of blood flow through each vessel is being reduced. Slower, 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 slower. So if you just look at the aorta and how fast blood is flowing through it, and you compare that to how fast blood is flowing through an arterial, it is moving way faster through the aorta. But remember, we're talking about the entire volume of blood moving through the aorta at a rate of 5 liters per minute. Do you have 5 liters per minute going through one arterial? No, you have 5 liters per minute going through all arterioles at the same time. You're spreading that blood out. That 5 liters that went through the aorta is now spread out over gazillions of arterioles. So inside of each one of those, the speed or the flow rate is really, really slow. And why do we want blood flow to be really slow through the capillaries? I mean, just trickling through. We need time for gas exchange, for nutrient exchange. So the velocity starts out really high. As you start spreading that blood out over more and more branches, more and more vessels, the velocity inside of each one of those vessels is reduced, reaches a minimum at the capillaries, but then once you start converging, it starts to go back up, right? Because that blood that was spread out over gazillions of capillaries is now going through fewer and fewer veins, right? So maybe millions of venules to thousands of medium-sized veins to other way, thousands of small to hundreds of medium to 2 large at the end, something like that. Why is it, though, that the velocity starts at 50 when it's coming through the aorta, but when we get to the vena cava, plural, it's half of that? What would happen to velocity if those 2 vena cavae converged onto a single last vein? Then what would the velocity be in that single last vein? 50. It's because there's 2, right? 5 liters per minute is going through a single aorta. 5 liters per minute is going through the 2 vena cava. So we're spreading that same volume over 2 vessels, so the actual velocity in each is half. But if we converged those into one, then yeah, the velocity would go all the way back up to where we started at 50. An analogy I often use, I don't know how good it is, but comes to mind for me. You're at the top of the driveway, and I think of this when I wash my car outside. So you've got the hose at the very top of the driveway, and you set it down, and it's on full blast. And water is coming out of that hose at a very high velocity, huge volume, high velocity. But then it starts to spread itself out over the entire driveway. And then you look down at the sidewalk, and water's just kind of trickling over the edge of the sidewalk. Why is it coming out of the hose so forcefully, so quickly, but then trickling down the sidewalk at the end? Because you've taken that whole volume of that whole volume of water. I have a haunted house. That whole volume of water that's coming through that single hose has been spread over the entire driveway and trickling down that entire sidewalk. But if you were to collect all that water and funnel it into a tube once again, the flow rate would go right back up to where you started. I washed my car with blood.
Here's what it helps.
Things you think about.
Do you have a red car?
That's how I keep it red. Ow. Shiny. So we have large arteries, medium, and small arteries, and I'll group those together. Arterioles. Large arteries, medium, small arteries, arterioles. They have nicknames, both functional nicknames and anatomical nicknames. And you do need to know what those names reflect. Don't memorize them, understand them. For example, why would we call the large arteries elastic arteries? It's an anatomical nickname.
They can stretch.
They have a very high proportion of elastic tissue. They are very stretchy. And the reason we want them to be very stretchy,
So you can recoil back.
they are subjected to really high pressure. And that really high pressure will distend the very thick-walled aorta. Now, if it was a vein subjected to that same pressure, it would probably explode. Right? But the wall of the artery is much stronger, much more durable. It's thicker. There's tons of smooth muscle, lots of elastic tissue. It's not as easy to distend. But it is distensible, right? You can expand it. You just need a lot of pressure. And that's where we have the highest pressure, leaving the heart, entering the aorta. Now then we use that elastic tissue, we use the fact that it will recoil to continue to move blood downstream to the capillaries, even when the semilunar valve is closed and blood is no longer coming into the aorta. It will continue to recoil and push blood downstream. The other nickname, functional nickname, is conducting vessel. So why are large arteries conducting vessels? What's their sole purpose? To conduct blood away from the heart towards the capillaries. We're not even manipulating the diameter of the large arteries. We don't constrict, we don't dilate. The diameter is pretty much the same all the time. We don't start constricting and dilating until we get closer to the organs. And then we have to decide how much blood does this organ need, how much blood does that organ need, and we can make adjustments to flow. So the next one. Oh, before the next one. This is what I was waiting for. All right, so here we're just looking at some names to give you an idea of what is a large artery, what's a medium. Aorta, a large artery, obviously, the largest. The main branches off the aorta, still large arteries. The branches off of those branches, now we're getting to medium-sized arteries, which we can also call the muscular arteries. So, ulnar, radial arteries, for example, those are muscular arteries. Hepatic artery proper, the artery that brings oxygenated blood into the liver, that's a muscular artery. Question?
So is it structurally different, like say from the arm to the leg, or
Yeah, and what tends to affect, so if you're talking the exact same size vessel,
when you're holding like a blood pressure measure in one area of the body and the other area,
yes. So the distance that blood has to travel to get from the heart to the brachial artery in the right limb versus the left, the distance can be a little bit different. A other than that, the size of the vessel should be about the same. So it's really the amount of resistance that the blood has had to overcome to get there. So if there is a difference in distance, there should be a slight difference in pressure. Does that make sense? Because the further you get from the heart, the lower the pressure is going to be.
Could we maybe misdiagnose hypertension?
That's why we tend to always measure from the left side. So just for consistency's sake. So all the norms, all the normal values that we use as a reference are based on left. So almost always when you're getting your blood pressure measured, they're going to put the cuff on the left side, not the right. But they shouldn't be that different. Right? And you guys can experiment with that. We'll play around with the blood pressure cuffs. You can compare right to left. They should be very, very similar. It shouldn't be the difference between one reads normal and the other reads hypertensive. It should not be that different. If it is, that tells me that you've got an anatomical problem going on.
There's
Right?
like 5 cups, so I was wondering, like, I never thought about the pressure differences. So it would be much different with thigh, or?
Oh, thigh? Yeah, because now you're getting a lot further away from the heart. Now, if it's still similar in size, the artery itself, and if the total distance blood has traveled isn't that different, then the pressure shouldn't be that different. Gravity, too. Gravity can play a role. So if you're going to measure from the thigh, you should probably be laying horizontal so that you don't have the additive effect of